Welcome back. Today we're diving into Section 5, Cables, Glands, and Terminations. Specifically, we are looking at Episode 5.1, The Wiring Has to Hold Up Too, covering cable specifications, earthing, and gland selection. Let's get right into it.
You can pick the absolute perfect XD flame-proof motor, or carefully select a highly rated XI barrier and still create a massive hazard if the cable feeding it or the gland sealing it just isn't built for the job. The best equipment absolutely fails with the wrong cable. Imagine a high-voltage power line leaving a nice, safe switch room, crossing a harsh, weather-beaten open deck, and then dropping straight down into a highly volatile Zone 1 pump room. That cable is going to face mechanical stress, chemical exposure, wild temperature swings, the whole shebang. If it's not perfectly specified for that exact hazardous environment, it literally becomes a conduit for disaster.
So here's the deal with the concept of a certified system. In hazardous environments, the electrical wiring, the glands, the earthing, they are not just afterthoughts or accessories. They're integral, highly regulated components of the explosion-proof system. IEC standards and offshore regulations essentially say you cannot separate the equipment from its wiring. It's all treated as one continuous, certified chain. And you know how the saying goes, the weakest link is the one that'll cause a spark.
Okay, let's strip back a compliant Zone 0 or Zone 1 cable to really see its anatomy. You definitely can't just run standard industrial wire here. The rules are strict. First off, you need an outer, non-metallic, impervious sheath to fight off chemicals and moisture. It also has to have a flame-retardant material marking. Beneath that jacket, you must have continuous metallic armor or braiding. And of course, there are minimum conductor sizes applied. That metallic armor actually does heavy double duty. It gives you vital physical protection against impacts, and, as we're going to see next, it acts as a mandatory electrical grounding pad.
This brings us to why that metallic armor is absolutely crucial. Think about the difference between poorly earthed armor and proper equipotential bonding. First, consider poorly earthed or floating armor. In a hazardous area, floating metal can build up a static charge or create a potential difference compared to the surrounding structures. It's essentially a static ignition risk just waiting to discharge a spark into a flammable atmosphere. Yikes, right? But then look at equipotential bonding. When that armor is securely bonded to the vessel's hull earth, it completely neutralizes that static discharge risk and ensures your system stays safe.
To make sure we get that right, there's a very strict earthing bonding rule we have to follow. Step 1. Technicians must properly strip the outer sheath to expose that metallic armor. Step 2. Connect that armor directly to an earth terminal using specific corrosion-resistant clamps, no standard solder here. And Step 3. The absolute golden rule, you have to bond it to the hull's equipotential system at both ends of the cable run. Doing this guarantees electrical continuity and completely wipes out those dangerous potential differences across the facility.
All right, transitioning into the Zone 1 X-10 enclosure. We've got our perfectly armored, flawlessly earthed cable, and it's finally reached its destination. But now, we have to actually penetrate the wall of a hazardous Zone 1 flame-proof enclosure without compromising its integrity. Honestly, how we seal this entry point is arguably the trickiest part of the entire run.
Luckily, the IEC 60079-14 standard gives us a very specific gland selection flowchart to follow for this. First, you identify the zone, in this case, Zone 1. Second, you check the enclosure volume. Is it greater than 2 liters? And third, check the gas group. Is it IIC? Now, usually in Zone 1, you need a robust, certified compound-filled barrier gland, but there's an exception path. If the gas group is not IIC and the internal volume is smaller than 2 liters, you can actually use a standard elastomere compression gland instead.
If navigating that logic feels a bit dense, let's think about it like airport security screening. Imagine a small carry-on bag where you know exactly what's inside. That's our small, non-IEC enclosure. It gets a quick check, which is our standard compression gland. But if you have a massive checked bag, or one with unknown high-risk contents, meaning an enclosure over 2 liters, or an environment with highly explosive IEC gas, you have to do the full screening. That means using a certified compound barrier gland. Basically, size and risk both drive how thoroughly you must screen and seal that entry point.
Okay, quick pop quiz to see if we're on the same page. Let's say an X-Deck junction box has an internal volume of 1.5 cubic decimeters. It's in Group 2B gas service, and it's located in Zone 1. Based on the rules we just went over, is a standard compression gland allowed? What do you think?
The answer is yes. You can absolutely use the standard compression gland here, because both exception conditions are met simultaneously. The gas group is IIB, which is not that high-risk IEC category, and the volume is 1.5 liters, which sits nicely under the 2-liter limit. But, and this is a big but, if you change just one of those variables, like if the plant suddenly upgraded to handle IEC hydrogen gas, boom, no way. You'd instantly need to rip that out and install a barrier gland.
Moving along, as our cable travels across the facility, it obviously crosses physical zone boundaries. Safe physical boundaries depend entirely on sealed cable routes and adequate ventilation. Because the cable physically crosses from, say, a hazardous zone into a safe control room, the route itself can accidentally become a superhighway for flammable gases. We absolutely have to meticulously seal that route, so gas physically cannot travel along the outside of the cable jacket or through the conduit into a safe area.
So how do we cross these boundaries safely? Well, you can't just drill a hole in a bulkhead and shove a wire through. The codes mandate specific methods. We're talking gas-tight cable transit frames. In some spots, sand seals or mortar sealing are required. If you're using rigid metal conduit, you need conduit sealing fittings packed with a non-shrinking compound. This totally stops a terrifying effect called pressure piling, where an explosion travels down a pipe, compresses the unburnt gas ahead of it, and triggers an even more massive secondary explosion. And finally, maintaining a static overpressure in safe areas ensures that if there is a leak, clean air pushes out, so the hazardous gas can't push in.
Now let's totally shift gears and look at intrinsically safe, or IS, versus non-IS segregation. Notice how the entire protection philosophy flips here. For standard, non-IS heavy power cables, the goal is containment. We are trying to confine the electrical energy inside the equipment to prevent it from igniting the environment. But for IS cables, the logic is inverted. The circuit is already designed to be so low energy that it simply cannot spark. So our goal isn't to protect the environment from the cable, it's to protect the safe low-energy IS circuit from the intrusion of outside energy. If a massive power cable shorts and dumps energy into our delicate IS cable, our safe circuit instantly turns into a lethal ignition source.
Because of that exact risk of energy intrusion, intrinsically safe cable rules are absolutely uncompromising. First, there must be a minimum 50mm physical air gap from any non-IS circuits on a cable tray. If you can't manage that distance, they have to be separated by a solid earthed metallic partition. Also, IS and non-IS conductors absolutely never share the same outer cable jacket. No exceptions. And finally, to make sure nobody ever gets this wrong, terminals, enclosures, and cable sheaths must be marked light blue. It's a vital visual mnemonic yelling at everyone on the rig, hey, this is an intrinsically safe system, keep the high voltage away.
Which brings us to a final thought to wrap up this explainer. You can engineer the perfect intrinsic safety loop, but your XI barrier is truly only as safe as the 50mm of air separating it from disaster out there on the deck. The wiring really does have to hold up, so it begs the question, when was the last time you actually walked the plant and checked the segregation on your cable trays? Thanks for hanging out with me for this explainer. I really hope this structured look at the source material helped clarify the intense world of hazardous area wiring. Keep learning, stay safe, and I will see you in the next one.